Today we will see specific analysis techniques. I said this is specific because each technique is not meant for all circuits. Each technique is meant for only few circuits. In other words, specific circuit can be analyzed with a specific technique. That's why I named this circuit as or analysis as specific analysis techniques. Whereas in the previous we studied general analysis techniques. That means any circuit for anything. So look at here, KVL, KCL, mesh nodal analysis are general methods of network analysis. So one class we studied KVL, KCL, another class mesh nodal. Then topology also we studied. They all come under general analysis techniques. By using the above techniques, we can find unknowns, voltages and currents for any circuit. Therefore, they are called general analysis techniques. But for some specific circuits or networks, we require specific or special analysis techniques. They are none other than network theorems, source transformations, star delta transformation. That means in some circuits we can apply theorems, in some circuits we can apply source transformations. Source transformation means voltage source, current source, voltage source is transformed. Similarly, a star network is converted into delta network is converted into star network for the sake of ease of analysis. So when you want to make the analysis easy, we can use these special techniques. They are not as general as KVL, KCL or mesh nodal. They are specially for few circuits. So let's see what are the theorems in that first today. Network theorems are, there are 10 theorems I have listed. Some syllabus are very vague and they may list or they may not list. But it's good to study all the 10. Some theorems we will study detailedly or more problems. But few theorems will just illustrate with an example and leave them. That's a basic idea here, not to study all the theorems in detail. Then all these theorems I have classified into 10. The first 5 belong to one slot. Thevenin's, Norton's, Millman, duality of Millman, then maximum power transfer. All these 5 belong to one category. Broadly they belong to Thevenin's theorem. Therefore, today we will be concentrating on first 5. And as I go along, you will be knowing how they are linked together. What way they are related, you will be knowing it. That's why wantedly I have put first 5 as a single slot. Then let's go to details. The first theorem is Thevenin's theorem. Please remember, in these theorems there are 3 important things you must know. The first thing is the statement of the theorem. Second thing is the conditions and constraints of the theorem. Under what conditions and what constraints this theorem is valid. Thirdly, applications. Sometimes all these 3 may be put into one statement. But observe whether all these 3 are being covered or being learnt. So first thing, I am going for the statement. For a circuit having more fixed elements with a variable load can be replaced by its equivalent Thevenin's voltage in series with equivalent Thevenin's resistance RTH. So when you have a fixed circuit like this, we can represent that as Thevenin's and Thevenin's. So voltage and impedance in series. This of course load. As you understand in the statement, the circuit must be fixed. Then only load is variable. Therefore, when circuit is fixed, you can apply this theorem. I'll give some examples. look at the conditions. The circuit elements should be fixed. For example, if the circuit elements are changing every time, better apply mesh or nodal. You don't need to go for Thevenin's and waste your time, because all that we try to do will become useful only for that one. Next one again we have to do it. That the very purpose of circuit is fixed is theorem. If circuit is variable, go for mesh and nodal. Secondly, the load should be variable. What are the applications of this theorem? I gave an application. The best application I gave is transmission lines. For example, there is a line, transmission line. Let us talk about electrical line, for example, power lines which carries electricity from Vijayawada to Hyderabad. So from Vijayawada to Hyderabad, you will have a big line. I am saying Vijayawada because VTPS. From Vijayawada thermal power station to Hyderabad distribution station, you have a big power line. That transmission line you can draw equivalent circuit, that's a Thevenin's equivalent once in a while. Even if it takes 1 month time to get the Thevenin's equivalent, doesn't matter. That's the meaning. So even if it takes 1 month to analyze it, it's a worth of it, because you can have Thevenin's equivalent and the load is always changing. Why do I say load is changing? For example, this year there are 1 lakh customers. They become the load. Next year 2 lakhs customers. Their houses are there and they need electricity. So load is always going on changing. As the load is changing, but the circuit is fixed, so analysis I can easily do it in one step. That's why the best application I gave was transmission line. The second application I gave is a vocal cord. This vocal cord I mean. When you see the vocal cord from the lungs to here, that also you can have a transmission line. It is just like a mechanical vibrations are coming and converted into speech. We call from the lungs to here, that's a Thevenin's equivalent you can draw and put the load as the tongue. So this is how we can really say this Thevenin's theorem is everywhere. And this tongue is actually acting as antenna. Therefore, Thevenin's theorem is being used everywhere, including vocal cords. You can draw the electrical equivalent of a vocal cord and then make it, that will become the voice cord also. So like this, applications are so many, but I just mentioned few to really get the idea of it. So finally, the vocal cord is fixed. Therefore, that doesn't change. So this is how, wherever the circuit is fixed, you can always talk about Thevenin's comes into picture. Then, how to calculate Thevenin's voltage? Look at here. While finding the equivalent voltage in any circuit, we have to make the load open, because we are seeing across that. For example, here, if you are calculating V Thevenin's here and then calculate how much voltage is coming. Very important thing that you must know here, in this branch there is no current. When there is no current in this branch, what is V Thevenin's here? It is as good as here. Why there is no current in this? Because it is open circuited. So V Thevenin's is nothing but open circuit voltage. So any series branch, there is no current here, so across this means, after all, direct answer V by R1 plus R2 into R2 is the Thevenin's. Then calculating R Thevenin's. When you are calculating any impedance, there are some few rules you can follow. Make all the sources inoperative. That's very important. You know why? Just like an idea saying, suppose you want to know the student's capacity, and when he enters the exam hall, we should remove the books. Then he is independent of source. Similarly, you should not allow the teacher into the exam hall. Therefore, just like a voltage source became inoperative and the current source becomes inoperative and the circuit becomes as it is. The actual impedance of the circuit comes when the voltage source is short circuited current source is open circuited. Why should we short circuit voltage? If you say voltage is not working, that means the voltage is zero. Zero voltage means short circuit. When you say current is zero, that is open circuit. Therefore, this became a very famous rule. Make the circuit independent of voltage and current means short circuit voltage, open circuit current. It is just like I said, let not the student enter with the books and teacher, let him come himself. What happens if we allow the voltage source and current source? Different current sources, different voltage sources will have a loading effect on the circuit. So that the actual impedance that you are looking here is not the real impedance of the circuit that being loaded by the source. That's why we want to know the actual impedance, means make these sources ineffective. Same logic for students into exam hall. If you allow teacher, somebody may come with a bad teacher, somebody may come with excellent teacher, therefore the performance completely changes. So therefore Thevenin's idea is, when you are calculating impedance, see that sources have become inoperative. That's the meaning of it. And calculate across the same load. That equivalent resistance is called Thevenin's resistance. But very important precaution, very important warning, this short circuit voltage source, open circuit current source is valid only when the sources are independent. If the sources are dependent, you can't use that technique. Why? If you say voltage source is short circuit, any dependent voltage source is shorted, that has no meaning. Why? Because this is depending on something else. So anything depending on something else, how can you really do it? Therefore, this short circuit and open circuit concept is basically for independent, please. For dependent sources, the Thevenin's impedance is nothing but Thevenin's voltage by Norton's current. That important precaution we have to follow. Anyway, I will be illustrating in problems, if not today, in the next class. And there is a third option also. So when you are calculating Thevenin's impedance, there are three examples or three approaches or three styles. The first style is all sources are independent. Second style is independent and dependent source. Third and the last style is no independent source. That rarely came. That was already asked in the exam. You need to be very careful. So as I deal with these three types of Thevenin's and Norton's, so please follow and understand what to do. So this is basic definitions of VThevenin's, RThevenin's. Let me take an example. I always like to give some illustrative example and then some testing. So first illustrative example. Find the load current for the circuit shown in figure. So this is a load current we need to calculate. This load current you can calculate using the Thevenin's, using the Norton's, or you can use mesh and nodal. But what is the difference between Thevenin's and mesh and nodal? If this total circuit is fixed, please calculate Thevenin's equivalent once in lifetime and then attach the load which is changing. If every time element changing, go for mesh and nodal. So look at here. This is basically solving using mesh analysis. Voltage minus R1 into I1 minus R2 minus into I1 minus I2. That's the first loop. Second, 0 minus R3 I2 RL I2 minus R2 into I2 minus I1. These examples, these are just like mesh and nodal, you can calculate. Solve for I2. When you solve for I2, that itself is IL. Therefore, you can also use mesh analysis for the circuit. In examination, you don't feel this, but in data application, it matters a lot. Because in exam, it's once for exam. But whereas in data applications, this circuit is going to be fixed, only load is going to be changed. Daily, some load getting added. But fixed circuit, you are calculating equivalent circuit. So once the equivalent circuit is ready, put the load, finish it off. That's the meaning of it. So I am now illustrating the same concept. You need to cross check at home how this separately by working yourself, how the IL that is achieved in mesh is same in Thevenin's, same in Norton's. So now let me talk about Thevenin's theorem. Same problem to calculate. What is V Thevenin's? As I told you, there is no current across this. Therefore, it is V by R1 plus R2 into R2. Look at here. That's the meaning. Whatever the current you get, that's what then V Thevenin's will come. Then what is R equivalent? When you want R equivalent, what did I say? The voltage source has to be short circuited. When you short the voltage source, automatically these two come in parallel plus this. Please remember, this is not coming into Thevenin's voltage, but this is coming into Thevenin's impedance. So R1 parallel R2 plus R3, that's impedance. Okay. Now whatever the voltage you got here, whatever the R equivalent or Thevenin's you got here, then calculate IL. And once, let there be a very big circuit, as I said, from Vijayawada to Hyderabad, a big circuit. All this we put into simply these two elements. Then load is here. Therefore, IL is equal to V Thevenin's by R equivalent plus RL. So that is how we can simply, within a fraction of a second, you can get the current. So if the equivalent is ready, you can always put the RL and get this current. This is about using Thevenin's, how to solve the problem. Then I am taking you to Norton's theorem. Norton's theorem is just the same. Conditions are also same. What are the conditions, please? The total circuit should be fixed, only load should be variable. These are the only two conditions for Thevenin's and Norton's. And as I have shown here, fixed circuit, and you have R Thevenin's here, short circuit. So short circuit current is Norton's current, this is R Thevenin's. One important observation, R Thevenin's is the same, that's why I have written R Thevenin's. That means whatever the Thevenin's impedance we achieved there, the same thing is valid here. Though we call it as Norton's impedance, it is the same. So impedance wise there is no difference, but there is a current wise there is a new thing. This current is from achieved by short circuit. That means short circuit the load, you will achieve the current. So this is Norton's theorem. In other words to say, if you get the Thevenin's, Norton's is ready. If you get the Norton's, Thevenin's is ready. Sometimes, in BTech exams, people used to ask Thevenin's as well as Norton's. You don't need to be shocked. You don't need to feel big problem, because Thevenin's and Norton's both are same. Only thing is, one is shown as a voltage source, other is shown as a current source. In one word to say, they are just like conversion from voltage source to current source and vice versa. So this is what I mean by the word Thevenin's and Norton's theorem. What are the conditions? Same as previous. Norton's theorem is dual of, see, those two are duals. As I said, duals means voltage source is dual for current, current source is dual for voltage. Now third theorem, Millman's theorem. People normally think this is another theorem, but actually it is the same as Thevenin's. What is the main idea here? Suppose if a circuit has voltages, sources V1, V2, V3, so on Vn, and the series impedances are Z1, Z2, Z3, so on Zn. Please remember, all these are connected in parallel. When voltages are connected in parallel, what is the effective voltage? Whichever is the lower. Remember always one statement in circuit theory. In series, least current flows. In shunt, least voltage exists. So whenever you are connecting voltage sources in parallel, you are no way going to increase the voltage. Then what is the purpose? The purpose is not to increase the voltage, purpose is to increase the current. So please understand, the Millman's theorem is not belong to circuits. Millman's theorem is nothing but Thevenin's, but not for the circuit, but a parallel combination of voltage sources. Let me illustrate. Look at this. Voltage source, impedance, voltage source, impedance, voltage source, impedance, then so on. So if you look at these voltage sources, try to calculate Z Thevenin's. or Z equivalent. We call Z equivalent Z Thevenin's. What is the rule for Thevenin's impedance? All the voltage sources must be 0. 0 volts means short circuit. When voltages are shorted, how are these impedances connected? Parallel. Parallel impedances, whenever they are connected, the best way to calculate the overall impedance is simply addition of admittances. So add the admittances y1, y2, y and so on. And therefore, y equivalent is admittances, Z equivalent is 1 by admittance. So this Thevenin's equivalent is nothing but here. Then what is voltage equivalent? Voltage equivalent is nothing but total current by admittance. Total current, how do we get? V1, Y1, V2, Y2, V3, Y3. Like this, if you add, you will get voltage equivalent. Therefore, the voltage equivalent is available. Current. Directly you can substitute or you can just follow Thevenin's. By mistake, if you forget in the exam, don't worry. Just apply Thevenin's, you will get the answers. And what are the conditions here? As I told you, conditions and applications are very important in competitive exams. Generally in our BTech, we will normally ignore because that's the first time experience. But later you need to remember. So what is the condition? As I said, multiple voltages is there, and when they are having some series impedance along with it, you need to calculate. Thevenin's, Millman is nothing but Thevenin's. Then let's go for duality of Millman's theorem. When duality of Millman's theorem, look at this circuit, they are all connected in series. When they are connected in series, what is happening is total voltage increase. As I told you, in series you can never increase current. Only voltage can be increased. For example, call this is V1, V2, V3. When you really call this V1, V2, V3, okay, then the total impedance we need to calculate. For example, as we already discussed, while calculating impedance, all current sources are open circuit. Now, if you open these current sources, what is the total impedance? Simply, they are in series. They are in parallel, but this is in series. So, Z1 plus Z2 plus Z3. That's the answer. I already have shown you. Then what about voltage? Voltage is nothing but I1 Z1, voltage 1, voltage 2, voltage 3. Then what is the final current? Current is always voltage by impedance. Therefore, you get ISC here, you get Z2. This is like a shunt. So please remember, Millman's theorem is just like Thevenin's. Duality of Millman is just like Norton's. So with this, we have finished 4 theorems already. Let's go to the last theorem for today. Maximum power transfer theorem. See, this is also, when we look at the idea, for a equivalent Thevenin's network, the maximum power can transfer from the source to the variable load when dPL by dZL is 0. Please remember, whenever we talk about maximas and minimas, we differentiate. This is a general question that everybody is asking, sir, why do we differentiate? That see, whenever you say maximum and minimum, if the differentiation is 0, if the difference is 0, automatically that has reached the maximum level. Suppose if it is further reaching, it cannot be 0, no. The change is 0 means no further change. That's why for maximas and minimas, we always go for differentiation. So this is power and this is impedance. So when you differentiate and find out, you will get the actual answer. So look at here. First case, when source impedance is pure resistor, this is resistor, and this is also a pure resistor, what should happen? Now you should differentiate with respect to RL. There you have done with Z, now you should go with RL. If you calculate the power and calculate dou P by dou L, dou RL, you will get R is equal to RL. That means the maximum power is transferred when these two are equal. Case 2, For example, if the impedance is Zs plus Jx, that is the source, load is RL plus JXL. As we already said, Zs has to be fixed, but the load is variable. In such case, if you differentiate with Z, you will get complex conjugate. So please remember, complex conjugate is the point. And very serious thought I have to give you. Please look at this. This is voltage source in series impedance. This is load. Some people by mistake they are thinking I am connecting the load to the source. Generally, rarely we connect load to the source. We always have a big circuit and then we connect the load. That means this is not the source actually. This is nothing but Thevenin's voltage and Thevenin's impedance. So in other words to say, this is not a voltage source, it is equivalent of a voltage source of something, a big circuit. This is, for example, as I told you, if you talk about a transmission line, take for example called telephone. Telephone has an impedance. That impedance is the load for the circuit. And from one place to the other place, there is a big telephone line. And telephone line, you can draw the Thevenin's equivalent for telephone line. And with that voltage, then you put your telephone line, then you can say maximum power is transferred or not. Maximum power will be transferred only when the impedance is complex conjugate. Otherwise, in other words to say, if you take the magnitude, complex conjugate will have the same thing. For example, 2 plus J3 magnitude is equal to 2 minus J3. So complex conjugate indirectly says magnitudes must be equal. So if you apply these two techniques, but the most important idea is this is not a source, this is not an impedance. They are the Thevenin's equivalent, Norton's equivalent of a big circuit. Let it be a telephone or let it be a loudspeaker. Even if you connect the loudspeaker to a very big line, the equivalent you have to see, if this impedance and that impedance are matching, then only the maximum sound will come. So maximum power transfer theorem is a very important thing. Suppose having done all these Thevenin's are equivalent, getting ready or got ready, then if the load is not matching, the whole purpose get wasted. Therefore, remember, maximum power transfer is possible only when the equivalent impedance of the circuit is equal to load. That's called matching. Maximum power is transferred. So this is the second case. Third case is also there, general. So there are, even I can tell you, there are two cases. If it's both are resistors, just equal. If both are impedances, complex conjugate. But if something else coming, don't worry, take direct magnitude. If you remember magnitude, that's more better. That anyway I'll cover in the problems, you will understand. So this theorem is applicable for only when the load is variable. When the load is variable, as we have been discussing in all this, remember this is the condition. Now I am going to take you to problems. There is a very important trick that I am going to play now. The problem seems to be like maximum power transfer theorem, but I am going to do like Thevenin's. Because I already told you that impedance is equal to Thevenin's impedance. So many people, they see the problem, they see they think it is a maximum power transfer theorem. Some people are thinking, sir, maximum power transfer, I'm not confident. There's nothing to be confident here. If you know Thevenin's, you know maximum power transfer. So simple. And if they're asking what is the impedance available, what is the impedance required for maximum power, just calculate Thevenin's and say this is it. So Thevenin's impedance is going to play a vital role in the exam, total exam. Because there is another thing, they can't ask you both. If they ask you Thevenin's impedance, Thevenin's voltage source and the maximum power, it becomes a big problem. That's why please observe as I go along, 90% of the problems of maximum power transfer I am going to do like Thevenin's. That's why I said all these 5 theorems are one slot. Other 5 I will deal in a second class, next class, but I don't want to deal here because I don't want to mix them. Now, let's go to problems. The first one, calculate VThevenin's for the circuit. Shown. This gate 1999, 2 marks is given. Is why 2 marks is given? After all, please remember, whenever AC is included, normally they give 1 extra mark. For example, the same circuit with resistors, you can have only 1 mark. So because AC is involved here, he is kind enough to allot the marks because they know how to give 2 marks and when to give 1 mark. Ready? Let's go. So if look at this circuit, J2, J5, J4, they are the impedances you have. Then one thing here, they already converted it. You don't need to convert into impedances. You know why? Because if you are converting into impedances, you need frequency. Frequency is not in the data. If the frequency available, you can say omega L 1 by j omega C, j omega L, you can convert yourself. So this is a mandatory, or you can take it for granted as you go along with the examination. Wherever frequency is missing, you will have impedances directly given. So let me take you to the solution. Look at this. I took the same problem here. It's very important. Please observe. This is 100 angle 0. Here it is the same, here it is the same, here it is the same. And we want VThevenin's. Say this is another node. All this becomes ground. So if you apply Kirchhoff's current law, KCL here, VThevenin's minus 100 angle 0 by 3 ohms plus current in this, VThevenin's by J4. Just with that equation, you are going to solve it. And all the circuit is going to be wasted. So don't be frightened looking at the circuits. You should know how to escape it. So once again, I am telling here, as you observe, suppose if I say VAB by J4, VAB minus 100 angle 0 by 3. If you calculate, you will get this answer. What a simple thing. Though the circuit is so big, so answer is A. So look at your options, you can see the answer is A. Let's go to second. Now I am back to maximum power transfer. I am going to do problems on all these 3 theorems. First is illustrative examples, then maybe I can do more later in the next class. The question is, calculate R to transfer the maximum power to the load for the frequency of 10. Gate 2001, 2 marks EC. And this is basically mentioned in this. Look at here. As I told you in the previous problem, this is 1. This is 10. 1 Henry, you have to calculate it. You have to convert it. How to convert? J omega L. What's the frequency given? Please observe here, 10. The same 10, you can take it here. So this becomes J10. This already 10. So what should be the impedance here? According to maximum power transfer, this magnitude should be equal to this magnitude. You know why I am taking magnitude? Because he said the resistance is there. He did not say there is impedance here. If there is impedance, I would simply say whatever j omega L here, 10 plus j omega L here, 10 plus J10 here, therefore this should be 10 minus J10. But when he says resistor, I need to take magnitude. So observe me as I do it. I took omega 10, then I took J10. For maximum power transfer to the load, RL is equal to root of R square plus JX square. So 100 under root, you can say 10 root 2. This is the answer. So very simple answer. What did I do here? I'm just calculating Thevenin's impedance. You can also observe the source is becoming short circuited. When source is shorted, because while calculating Thevenin's impedance, we always say voltage source should be 0. Therefore, having made this as 0 and these two, that is, answer is simple. R is equal to root of 10 plus J10, means root of 10 square plus 10 square. This is the answer. So answer is D. Let's go to third problem. Calculate ZL for maximum power transfer to the load. To get 2003, 2 marks. As already told you, why 2 marks given? Because AC is involved. So one thing I have been telling from the beginning, AC and DC and dependent sources should be studied together. Good. Now, you look at this circuit. As if it seems to be a great circuit, very simple. You are opening here. When you open, what is the resistance you want to know? When you want to know the resistance here, please understand, as I told you, it is the Thevenin's impedance. And you don't need to calculate Thevenin's voltage. Actually, Thevenin's voltage should be calculated if they are asking for power. They are only asking for impedance. So why should you calculate and waste your time? So I am going to do one thing. For Thevenin's equivalent, I will short this, and these two comes in parallel. Very simply, if two things comes in parallel, you calculate the parallel impedance. So 6 plus J8 in parallel with 6 plus J8, calculate it. And take the magnitude, you will get the answer. Look at here. As I have taken 6 plus J8, parallel combination I took, I got 3 plus J4. If the load is impedance, I would say the answer is 3 minus J4. But the load, he said, is resistor. Resistor means you should take magnitude. So take the magnitude of this. 3 square plus 4 square is 9 plus 16 is 25, under root 25 is 5. So answer is 5 ohms. So just enjoy this concept. Just treat it as Thevenin's. That's why the problems, they all together under one heading, 5 theorems into one heading, that is called Thevenin's. Now let me take you to fourth problem. Calculate Z Thevenin's for the circuit shown in figure. Is directly coming, not like indirect way of coming to Thevenin's power. He is not asking for maximum power, direct Thevenin's. Z1 is here, Z2 is here, Z3 is here. He is asking for Thevenin's. What is the answer? When you want Thevenin's, what you should do? Short circuit this. Look from here. This two comes in parallel plus this. When you are looking from here, these two comes in parallel plus this. Right? That's the answer A. Now I am showing you. This source is short circuited. These two are in parallel. Add that. And finally, this is the answer. So, answer is A. So, this is a direct problem on Thevenin's. So, some problems are directly coming on Thevenin's, and Thevenin's is nothing but Norton's, and indirectly Millman and duality of Millman, and more serious thing is maximum power transfer. Fifth problem. Obtain Norton's current, only current you wanted. So when you want Norton's current, what to do? Look at here, you have to short it. If you short this, please observe. When you short this will go away. Whenever you short a parallel element, no current in this branch, so they'll go away. Now what happens? What is the impedance coming? What is the current coming into that short? Now please observe as I deal with it. Look at here. When I shorted, the parallel branch has gone. That's one important observation. Second observation is, I have converted this current source into voltage source. How to do it? Impedance is same, whereas voltage is current into impedance. 1625s are 400. So it is a 400 voltage source in series with 25 ohms, and then enjoy the circuit. Therefore 425 with this, and this is another. So what should be the current altogether? Very simple answer is 400 by 25 plus 15, that means 40. 40 ohms plus J30 is the answer. 400 by, so you look at here, 40 plus J30 is the answer. And if you do this calculation, you will get this one. So answer is A. So this is how we need to really use specific techniques. For example, already this is specific technique where it is applicable is Norton's. Into Norton's I have used source transformation techniques. That's why, as I told you, these techniques are star delta, Thevenin's impedance, and all that, they go together. Let me take you to sixth problem. Calculate R for maximum power transfer to the load. Again, it is maximum power. As I am telling, it's not the maximum power because it is the Thevenin's. Look at here. You need to calculate here. What to do? Voltage source, short it. Voltage source, short it. Current source, short, open it. So this is shorted, this is shorted, this is open. What is the impedance here? 10 parallel 10 is 5. Another 10, 15. The answer is 15. So simple. So enjoy the concept of Thevenin's. I'll show you for demonstration for your understanding. This I have shorted. This I have shorted. Here current source is open. So what happened effectively? 10 parallel 10 is 5 plus added. So total is 15. So answer is C. So like that you can comfortably do it. So that's why I have brought all the 5 things together. All these 5 theorems, they are together. You can use one and the other interchangingly and get the impedance altogether. Seventh one. In the circuit shown, if the voltage source is 100 angle 53.212, then find out the Thevenin's voltage. When you find the Thevenin's voltage means across this load. Okay, see there. The first thing is, please remember, there is a very important concept I am going to tell. Suddenly, dependent sources came. When dependent sources came, we have one understanding. Whenever you want the Thevenin's voltage, you can get. But if it is Thevenin's impedance, don't go for open circuit, short circuit, that's not valid. So here luckily this is only voltage. So what I am going to do now, I have to open this because we have to calculate across this. So open circuit impedance is called Thevenin's impedance. When you open this, automatically what happens is I2 becomes 0. If I2 is 0, this becomes what? Once, please observe. If this is opened, open means current 0. If I2 is 0, what happens to this? J40 into 0. That means this is 0. Voltage 0 means what? Short circuit. So when you short this, okay, these two elements are only there, this is not there. But this voltage will create a voltage here. This is called voltage is affecting here, this current is affecting. This being 0, this is shorted. Now I'll show you, observe my solution. Look at here. As I told you, as I2 0, this got shorted. Now what all that you need to know is, what is the equal voltage here? Please observe another serious matter. These two are open. When these two are open, the current in this branch is 0. And if the current is 0, the drop is 0. Therefore, the VThevenin's is after all here, just here. Whatever the voltage you get here is the VThevenin's. That means whatever the voltage you are getting here, multiply with 10, that will become VThevenin's. So good. Now please observe. What is the voltage here? Vs by 3 ohms plus J4. That's a current. Into J4 is the voltage. That into 10 will give you VThevenin's. So please observe my solution. As I said, as I've been talking to you, V by J4 plus 3 into this. So what is V there? 100 angle 53.2 by this. So you substitute here. So VL1 is, what is VL1? As I already told you, VL1 is basically here, this voltage by this plus this. So get only two steps. VL1 is Vs by this plus this into this, and that is multiplied with 10. That gives you Thevenin's. That is the answer. Answer is C. So though the problem seems to be very big, it's not as big as you think. You'll be wondering, such a big problem given for 2 marks. Anyway, in GATE exam, 2 marks is the highest marks. Even if you have 4 marks question, that is 2 marks each. So that's why that is the answer for this solution. 8th problem. Calculate Thevenin's equivalent for the circuit shown as seen at the terminals PQ. So don't worry about this circuit. Take it as a load, get the equivalent circuit. What is the equivalent impedance? First, better to calculate impedance. How is it? It is just like, when you are calculating impedance, what do we normally do? Whenever you calculate impedance, what you normally do is, you will take this circuit here. Simply, when you short this, when you short voltage source, this will go away. So you are left with these two. When you're looking across this, so 10 parallel 10 become 5. So this is the 5 ohms is the answer. So impedance is 5. Voltage anyway we can calculate. See, there also you can enjoy the ABCDs. If there is only 1 5, you can finish with one answer. But like unfortunately 2 5s are there. We need to confirm whether it is 4 or 2. For that we have to go for voltage. So when you calculate voltage, 4 by 10 plus 20 or 4 by 10 plus 10 into, that's why it is 2. So this is the answer A. Now look at 9. Very funny, very interesting. Again I am back to maximum power transfer. In the circuit shown in figure, the maximum power will be transferred to the load when R is equal to how much? As you know, this is given as 3, so total impedance must be 3. So simple. And the Thevenin's impedance is what? When you open circuit this and look from here, 10 and R parallel 6. Can you tell me one thing? As we have been following voltage source, you have to short circuit this voltage. Okay, good. When you short this voltage, these two are in parallel. Okay, so I am going to tell you very simply, R into 6 by R plus 6 is equal to 3. Why? Because parallel combination of R and 6 should be equal to 3. That's my answer is C. I'll show you the demonstration. As I said, short circuit here. These two are parallel, R into 6, R 6. So R 6R by R plus 6 is equal to 3. Cross multiply and solve it, you get the answer. So that is the answer called 6 ohms C. And we are coming to the another problem. Calculate IN, R Thevenin's for the circuit. This is taken from IES 2004 EEE. So he is asking for IN means Norton's current. R Thevenin's is same. See, whether it is Thevenin's impedance, Norton's impedance is same. So only difference is in Thevenin's we say V Thevenin's, in Norton's we say I Norton's. So what exactly, for example, straight away I will show you. If you are calculating impedance here, what is the answer? Tell me. So simple. Look at this. I am going to finish without solving anything because examiner is in trouble now. I mean, because he gave an option for us. Look at here. This is 120 voltage short circuit. And look from this. If this is short and this is short, these two come in parallel. If these two come in parallel, 40 into 60 by 100. 40 into 60 by 100 is very simple. 40 into 60 is 2400 by 100. 100 and cancel. Answer is 24. And he has done a mistake because he gave 200s but he gave only 124. And without calculating the answer, I am going to finish it because I don't need to waste my time in the exam. So such options normally you will get and enjoy that option. So with one answer, you will get the final answer without calculating the second one. That's the, look at my solution for you. So these two are here. These two you can short it. They come in parallel. When they come in parallel, you have 40 parallel 60, that is 24. But anyway, he asked for VThevenin's. No, I am calculating. How do you calculate this? This actually you can use Millman's theorem. As I already discussed, Millman's theorem is valid for two voltage sources in parallel. So this is the Millman's theorem. Voltage by impedance plus this voltage by impedance, because currents you are calculating, currents by total impedance, admittance. Current by admittance is voltage. So that is 96. So what is finally Norton's current? Norton's current is VThevenin's by RThevenin's. That means 96 by 24 is 4. Now if you go back to your options here, you see actually 24 is already answer. 4 is just a cross check. Otherwise, if you are short of time, you just put the answer B because 24 is available only thing. Actually, by solving this, it is confirming your answer. You will get confidence of no negative marking. That's why it's good if you have time, you solve it and get your confirmation well. So that's where we stop about these 5 theorems put together. I'll be back to you with some more examples of all the 3 styles. As I told you, all independent, independent and dependent, and only dependent. With that, we will have some more examples along with other 5 theorems to talk. So this is what it means by the concept of theorems. And we also have source transformation and star delta transformations are also involved in this topic. So this is the syllabus. These are the exam problems we did. As much as possible, I am always putting the previous exam problems into the lecture. But if they are not there anyway, I am adding my own problems. So finally, you must study the total subject and total width as well as the depth.